Welcome to a lesson with Dr. Powell. Let's take a look at graphing conic sections in polar coordinates. Now, graphing conic sections in polar coordinates is very nice, at least in the equation form. They'll all follow the same basic format. So let's get started. They're represented by a focus, a line called a directrix, and a ratio, which we'll call E for eccentricity. And this is going to be the distance where I'm at on the curve currently so here, suppose I'm drawing a curve right here. Maybe it's an ellipse, so it wraps around here. And maybe this distance right here compared to this distance, I'll call this a D and an R. Eccentricity would be this ratio. Now, R is very fitting because this is the origin. We're going to let the focus be the origin. And so R is the distance from the point in question to that place. This point could be labeled as an X, Y, and Cartesian coordinates. So now what is D? Take the X coordinate right here. Since that's R, let's think. R, this is X, this is Y. This is theta. X is going to be R times cosine theta, because if R were 1, this would be cosine, this would be sine, but multiply everything by R. So R cosine theta. So this X coordinate's at R cosine theta. And this X coordinate, let's suppose in this particular case, if we're describing something, let's just give an example. Let's suppose this line's X equals 3, which is to the right of the origin. Let's also, in this example, suppose that E is equal to 1/2. Okay, so it looks like the equation of this ellipse is simply determined from here. 1/2 is equal to R over D, but D is the difference between these two X coordinates. 3, which is to the right, minus R cosine theta. That is the equation of our ellipse. Now, solve for R. So we can multiply minus R cosine theta is equal to R. 1/2 times 3 minus 1/2 cosine theta, then we have an R still there, is equal to R. Add over to the other side. So we have 1/2 times 3 is equal to R plus 1/2 cosine theta R. And then we can factor out an R, 1 plus 1/2 cosine theta. And then in the end, we end up getting R is equal to 1/2 times 3 all over 1 plus 1/2 cosine theta. Okay, let's take a look at this formula just a little bit. Okay, so notice where the eccentricity is. It's right here. And right here. Now 3, that's the distance from the focus, which is the origin, to the directrix, this distance right here. Let's call that capital D. So really in the top we have E times capital D, and this is E occurring right here. Now if we were to change things up and put the directrix on the opposite side, the coordinate on the curve, the X coordinate, would still be X is equal to R cosine theta. The negative value is taken care of in the cosine, and this, say, is X equals -3. So this is to the right, and we subtract this. So you would have R cosine theta plus 3 as our distance d. Now, notice this is all positive. Last time we had a negative when we subtracted when we were on the other side. So this change in sign will actually affect things in the solving. So this becomes a negative. So if I were to make this a negative, I would actually get the exact same ellipse, except the directrix would be on this side. And so it'd be drawn differently. So it's the same ellipse, but instead of being over here, it's going to be over here in the relationship. So it changed where the directrix was located. The cosine tells me I'm dealing with x values. So what if we had r is equal to 1/2 times 3, and we had 1 plus 1/2 sine theta? Then everything would be the same, but with the directrix above at 3 again. And the ellipse would be drawn down here. If we had this, but we changed to a minus right there, it'd be the same, except directrix would be down here at y is equal to -3, wrapping around. So we get our position of our directrix from this sign and from this value, and also if we're in x and y by looking at sign. Now the eccentricity told us that we were dealing with an ellipse. That specifically with e being 1/2. Let's think why. At the vertex, let's see, we have something like this. So this means this distance will be 1/2 of this distance right here as we're drawing our curve. Now, the distance to the curve is always going to be one from the focus is always going to be 1/2 of the distance all the way over there. Well, eventually, if we went out way too far out here, if we go too far away, the ratio is going to get there's no way of making that work, because anything out here in relation to here is close in ratio to way over here. So we're going to have to double back at some point, so that the distance from here to here is 1/2 of the distance from here to here. So we get a doubling back thing when our eccentricity ratio when it's less than 1. So when e is less than 1, we have an ellipse. When e is equal to 1, we have a shape, which is a parabola, where the slope's always increasing as I go out. If e is bigger than 1, I get a shape that's 1/2 of a parabola, or hyperbola, I mean. Hyperbola usually has 2 parts. Now the difference between but we're only looking at 1/2 of it. But the difference between a hyperbola and a parabola essentially is that the slope eventually stabilizes or gets close to stabilizing in the curve itself. So eventually it will look like kind of like a straight line as it goes up for a hyperbola, whereas here the slope's always increasing. So with these 3 different types of eccentricities, we pretty much have all the equations of our 3 different types of conic sections: parabolas, hyperbolas, and ellipses. So if I wrote down r is equal to 10 all over 1 minus 2 sine theta, I would know that this would be of a hyperbola. His eccentricity would be 2. This would be 2 times 5, eccentricity there. So my directrix would be at a value of 5, but negatively and below, because it's sine, so y value. So the directrix would be down at y is equal to -5. This would be the focus. And I know I'd have a hyperbola. Now, the eccentricity tells me where my vertex is located. Notice how the eccentricity is 2. That means the distance from here to the curve is twice as much as the distance from that point to the directrix. D, R. So this is twice as much as that. This whole distance right here is 5. I know R plus D is 5. I also know that R over D is 2. So we could do this in a couple different ways. I could realize that this is going to be 2/3 of the way down from 5. So I could think of 2/3 times 5, so 10/3. So this point in Cartesian coordinates would be 0, 10/3. In polar coordinates, you could think of it as being 10/3, negative pi halves if you want, for the vertex right here of this hyperbola as it goes up. Or we could have solved this system right here, thinking of R as being 2D, plugging that in here for R, that is, and getting 3D is 5. So D is 5/3, and then taking 5 and then solving right here, R plus 5/3 is equal to 5, and subtracting, we get 5 minus 5/3, which is 10/3 as desired. Okay, so we can find a vertex in the following way, and we have from the hyperbola, and we could identify what shape it was and where it's drawn with respect to the focus and the directrix. Thanks for watching.